When we write electron configurations, we're writing where the electrons are, probably, in an atom. I assume that you've seen it before, but we do need to review what we mean by the S block, the P block, the D block, and the F block. Note that the element helium, up here in the upper right corner, is technically part of the S block, but it's put over here because it's also one of the noble gases. So you've got to put it somewhere. Helium has only S electrons, and so it technically should be part of the S block. Hydrogen, if we look on the left side of the screen now, hydrogen only has one electron, and that one electron is in the 1s orbital. Helium has two electrons, and they both can fit in the 1s orbital. Phosphorus has a total of 15 electrons. Get out your periodic table and find it if you need to. The electron configuration for phosphorus would read 1s2, 2s2, 2p6, 3s2, and the last three electrons would go in the 3p orbitals. What about the iron 3 ion? For these first three, we've simply picked the number off the periodic table because those are neutral atoms, and whatever the atomic number is for an atom, that's the same as the number of electrons. For iron 3+, the iron 3 ion, what I like to do is write out the electron configuration for neutral iron first, and then I'm going to take away 3 electrons, which will result in me getting from iron to iron 3. So let's do that. 1s2, 2s2, 2p6. We're starting at the top left corner of the periodic table, and we're reading it left to right like a book. And we're right now at element number 10, which is neon. And if you look at my laser pointer at the periodic table right here, that's neon right there. So now we go to the beginning of the next row, and that will be sodium and magnesium, so 3s2. Then we make our way over to argon by writing 3p6. Then we go to the beginning of the next row, which is potassium and calcium, 4s2. And then we need to write 6 3d electrons. Remember, when you go into the D block, you go down one principal quantum number. And that would be the electron configuration for iron. Plain old iron, neutral iron, 26 electrons. But we need to take away 3 of these electrons. So the question is, which 3 do we take away? And the answer is that the electrons that are lost first are from the highest energy level. The highest energy level here is the 4th energy level. So those 2 electrons go bye-bye. Now we start picking them off the end, and that means we need 1 of those 3d electrons. The electron configuration for the iron 3 ion will end in 3d5. We'll just give you a definition here at the end of this slide. The Aufbau principle says that electrons will take the lowest energy orbital that is available. That is how we know the order in which to read these electron configurations, 1s2, 2s2, and so on. Let's write the electron configurations for these ions. A neutral aluminum atom would read 1s2, 2s2, 2p6, 3s2, and 3p1. But this is an aluminum ion, so it's lost 3 electrons, and there they go. The oxide ion, let's start first with neutral oxygen, which has 8 electrons, 1s2, 2s2, 2p4. That's 8 electrons. But the charge shows that we've gained 2 electrons, so the electron configuration for the oxide ion is the same as that for the aluminum ion. We'll do the same thing with fluorine. Neutral fluorine has 9 electrons. There are 2, there's 4, and there's another 5. But the fluoride ion has gained an electron, and so the 2p orbitals have moved up from 2p5 to 2p6. Similarly with the nitride ion, neutral nitrogen has 7 electrons, 1s2, 2s2, 2p3, but we've gained 3 electrons. And what you can see here is that all of these ions have the same electron configuration, and we refer to them as isoelectronic species. Hund's rule says that each degenerate orbital must have one electron before any take a second. Now we need to know the definition of this word, degenerate. When you come home past curfew and your father uses that term, it means something entirely different. But in chemistry, the term degenerate means equal energy. For example, the 3p orbitals are degenerate. In other words, the 3p orbitals all have the same amount of energy. The 3p orbitals are not degenerate with the 3s orbital. The 3s orbital is lower in energy. But those 3p orbitals are degenerate. The 5 3d orbitals are degenerate. The 3 5p orbitals are degenerate. And what Fred Dog says, as we refer to him in the business, what his rule says is that each of these orbitals must have one electron before you start to double up. And in particular, they also have to have the same spin before we start doubling up. In other words, when we fill these orbitals, we have to go up electron, up electron, up electron, and then go down electron, down electron, down electron. We're not supposed to go up, down, up, down, up, down. That violates Hund's rule. Orbital diagrams show the spins of electrons and which orbital each is in. We show the spin by drawing an up arrow or a down arrow. Orbital diagrams very similar to electron configurations. An oxygen atom has 8 electrons, 1s2, 2s2, and then it ends with 2p4. What is tempting to do would be to draw in, for an orbital diagram, up, down, and then empty orbital. But that would violate Hund's rule. So the way we need to do this is we need to go up, 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 and then electron number 8 needs to go down. Could go anywhere in the 2p orbitals, but typically the one on the left is chosen. That's how you draw an orbital diagram for oxygen. Phosphorus is element number 15, and so the orbital diagram for phosphorus would go 1s2, 2s2. Now, when we fill the 2p orbitals, which we will, technically we should go up, 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 and then down, 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 to be consistent with Hund's rule. That gives us 10 electrons. We need a total of 15 because phosphorus is element number 15. So there's number 11, there's number 12, and then number 13 and 14 and 15, we need to make sure that those conform to Hund's rule. So in an orbital diagram, paired electrons are shown one up and one down. Those are called paired electrons. Unpaired electrons, they could be shown spin down, but typically they're shown spin up. An unpaired electron is when you only have one electron in an orbital. Valence electrons, and this is a definition, the s and p electrons only in the outermost energy level. Valence electrons can only be s and p electrons. D electrons are never considered valence electrons, neither are f electrons. The shorthand electron configuration is written using these rules. First, you put the symbol of the noble gas that precedes the element, and you put that symbol in brackets. And then you continue writing the electron configuration from that point until you're done. If you find element number 16, that is sulfur, to write the shorthand electron configuration, you find the noble gas that precedes sulfur, and that's going to be number 10, neon. So we put that in square brackets, and then we go over to the left side of the periodic table, starting with element 11, which is sodium, and we just work our way from that point to element number 16, which is sulfur. So we say 3s2, 3p4. Let's try one more example. Cobalt. Cobalt is element number 27. The noble gas that is nearest and right before cobalt would be argon. That's number 18. So now we go back to the left side of the periodic table where we have potassium and calcium. Those would be the 4s2 electrons, and then we go into the 3d electrons and count out however many it takes to get to cobalt, which in this case is 7.